Good afternoon, I'm Joshua C. Agar, and I'm here to present about the relative motion of bodies. So in this presentation, I'll be discussing the concept itself and some of its applications. Relative motion of bodies, in a nutshell, states that the observation of motion is always relative. There's always an observer observing the motion, and there's always the observed doing the motion itself. So in this example, for example, person A, who is stationary, just like us, staring at the screen, is observing person B moving at 40 kilometers per hour. Since person A is also stationary, from his perspective, he will observe that person B is moving at 40 kilometers per hour also. However, not all the times that the observer is stationary. Sometimes the observer is moving at a constant velocity. In this example, person B is still moving at 40 kilometers per hour. However, the person doing the observation, person A, is now moving at 20 kilometers per hour. So, from our perspective, person B is still moving at 40 kilometers per hour. However, in person A's perspective, he will see that person B is moving at 20 kilometers per hour, still going away from him. And there are instances, for example, where person A is moving faster than person B. Then, so from his perspective, in person A's perspective, person B is moving towards him at 20 kilometers per hour. So, there's an inkling about the math, so which is further discussed by Newton in his laws of motions and his applications of vector operations in describing the motions in general. So, for example, in a bus, person jumps at a speed of 1 meters per second. So that's with respect to the reference frame of the bus. The bus itself, however, in our perspective, is moving at 3 meters per second. So with as the stationary observer, moving at 3 meters per second. That's how we see the bus. However, the person who is doing the jumping at 1 meters per second, inside the bus that's moving at 3 meters per second, if we were to observe that scenario as the stationary observer, we will then see person A doing a diagonal path. So that diagonal path is described by the vector sum of the velocity of the person with respect to the bus and the velocity of the bus with respect to the observer. The same principle applies to the acceleration. So for example, person A is accelerating upwards with respect to the bus, then the bus is accelerating at a certain rate with respect to us, the observer, and what acceleration will we perceive in our perspective is that the vector sum of those two. So the same principle applies with acceleration. So also, of course, as the observer is also moving at a constant velocity. So our frame of reference, the observation point, how we see things, is also relative to, for example, in the North Pole, with respect to the North Pole, we are moving at a constant linear velocity. That is related to the angular velocity of the Earth, which is derived by 2 pi divided by 24 hours. So, we obtain our linear velocity with respect to the North Pole, then we plug that in along with the other vectors mentioned, so that we can obtain the velocity of the person with respect to the pole. So getting the velocity of the person with respect to the pole, we need to do vector operations concerning the velocity of the person with respect to the bus, the velocity of the bus with respect to us observing the event, and our relative velocity with respect to the pole. So the vector sum of those four is the velocity of the person with respect to the pole. That brings us to what's called the Coriolis Effect. So for example, if we're at the pole, so we're not experiencing any velocity. However, as we move away from the pole, since the Earth is moving at an angular velocity, our frame of reference also begin to move at a certain rate. So we get the moment arm, which is derived using this, so that we can obtain the linear velocity with respect to the latitude. So for example, at 80 degrees with 80 degrees north, this is the linear velocity. However, if we were to compare that with the linear velocity at 11 degrees north, which is farther away from the pole, you can see there's huge differences. So the frame of reference near the equator is moving faster than the frame of reference closer to the pole. So what are those implications? So for example, there's a parcel of air moving directly southwards from the pole towards the equator. The velocity that's initially set is with respect to the pole. However, the moving frame of reference would then result to that object, parcel of air for example, assuming a curved path. So the actual path is due to the changing velocities of the rotating reference plane. And we obtain, for example, the velocity of the reference frame. For example, if we're standing here with respect to the pole, we just obtain the opposite of that. So what, for example, the relative velocity of the pole with respect to our perspective at 11 degrees north is the opposite of the velocity of us with respect to the pole who's observing us also. And same happens if the parcel of air is now moving from the equator towards the poles. Same instance, due to the angular velocity of the earth, the parcel of air assumes a curved path. So if you were to track the actual path with respect to the earth, you can see that the path is curved. So that explains why the monsoon, the amihan and abagat, is always coming from the southwest or coming from the northeast. It is because of the rotation of the earth. So that brings us to another question. So with regards to the changing frames of reference, so how do we determine velocity? So do we take the relative velocity, or should we just do the absolute velocity? Classic example, or an appalling example, is in 1983. This is a Korean Airlines flight from Anchorage, Alaska to Soviet Union. The flight plan was just simple. So head 40 degrees south of west towards Japan. Then when you reach Japan, move west towards Seoul, South Korea. However, there's a disclaimer, or rather a warning. The commercial aircraft, must not enter Soviet airspace, or else they would be shot down. So it's the middle of the Cold War, so tensions are rising between the US and the Soviet Union. So they're trying to provoke each other, but not totally escalating into a war. So what happened is that during the flight, the autopilot system that the aircraft uses 4 basic control modes. Among the 4 is the INS, or inertial navigation system, which sets the bearing, the velocity, as relative to the latitude. So for example, it descends down the pole and adjusts its bearings, taking care of the inertial deviations due to the Earth's rotation. However, sadly, this is the ideal flight path. However, during that night, the heading setting was inputted into the controls. What happened is that the bearing presumed by the aircraft is absolute, so that's with respect to the pole. So it just presumed a straight path, not taking care of the changing frames of reference. So as a result, it veered off towards the Soviet airspace, ended up being shut down, so further escalating the Cold War, almost culminating into a nuclear war. As engineers also, we need to take into consideration and be careful in evaluating, of course, the motion of the objects that we're observing. So concrete structures, its vibrations. So we have to take care and know when to use relative velocities or absolute velocities. And that ends the presentation. I hope it's been fruitful with some of my examples. Thank you very much.